Well, here we've got a rate law problem, and in order to have a rate law, you need to have a reaction that's occurring, and the reaction that they have for a given temperature is this compound. With two carbons, you're talking about an ethyl group, and this bromine is added to it, so this is ethyl bromide, and it's reacting with a hydroxide ion to make alcohol and bromide ions. Ethyl bromide is a pretty nasty compound. It's one of the ones where you have to deal with a carcinogen. It's this bromine attached to the ethyl messes things up. And if you work with this, you really should be cautious. Make sure that you've got adequate protection. There's a controversy in terms of bromine compounds and hydrocarbons. There's a number of large hydrocarbons, some fatty acids that have bromine added to it, that are used in some types of sodas, and they're trying to ban those. They've been banned in Europe, and these brominated beverages are still allowed in the U.S., but there's a movement to get rid of them. So bromoethane, and you should know eth as being two carbons, but let's get back to the reaction. Here's the liquid, the bromoethane. I should have mentioned that it boils at a low temperature. Ethane is a gas at room temperature, but when you add the bromine to it, it becomes a polar molecule with a definite dipole, and you've got a larger molecule because of this bromine, and it turns into a liquid. Not a very good one. It boils at about 101 degrees, so you can almost hold this in your hand to make it boil, but don't. You want to breathe these fumes. And it reacts with hydroxide, becomes the non-dangerous alcohol. And here they've done a number of trials. They had 1/4 molar, so they had a solution of bromoethane, about 1/4 molar, and some hydroxide, a basic solution, 1/10 molar, a pH of about 13. And they found out that it reacted, that some of this bromoethane changed into the alcohol at a rate of 4.75 times 10 to the negative 4 molar each second. So each second, 0.0004 molar of these two compounds disappear, and our alcohol is made. But that changes with the concentration, because if we had concentrations of a half molar, notice the rate goes up. And here they have another concentration where we've got about a 1/3 molar, different rate, and then a highest concentration where we have both the bromoethane and the hydroxide increased, and we have a rate, this is caution, and it looks like it's less, 2.85, but it's times 10 to the negative 3 instead of times 10 to the negative 4. So I advise, because we're going to be comparing these rates, to readjust these numbers so you can compare them more easily, because that's what we're going to do. We're going to compare these rates with the concentrations. So I just put down 4.75, 95, 713, and I changed this to 28.5. So you can see that it's far more concentrated. We'll be comparing these numbers, so sort of setting them up as this simple value lets you see some comparisons, because you can see that 9.5 is double 4.75. You'll see that in most AP questions dealing with this type of a problem, that you'll be able to see multiples in terms of rate and even concentrations, and you should be on the lookout for that. Look out for doubles or triples, like here the concentration is doubled, and that's going to allow you to answer these questions more quickly. Now, what's the question going to be? Well, the major question is, what's the law that explains these rates with these concentrations? That's the rate law expression. That's a good name. Here's an expression. It says, if you want to know how fast a reaction is going in molar per second or atmospheres per second in concentration units, you will have a constant value that's always going to be the same, dependent upon one of the reactants, in this case the bromoethane, times the other reactant. We're concerned with the two reactants and their concentrations. Fortunately, you can ignore the products. They're just the ones that are going to be made, and it's the concentrations of the reactants that are critical. Now you'll notice I have a question mark here and a question mark here, because the key to these rate law problems, aside from having just the reactants in the expression, is the power that they're raised to. So we'll have the concentration of the bromoethane, let's say 0.25, and the concentration of the hydroxide, 0.1. But they will be raised to a power. Now, one of the nice things about rate law expressions that deals with why things have different rates is that these powers will be whole values, 0, 1, or 2, 98% of the time. It's possible to have a fraction, a half, or even a -1, but those are very, very unusual. So in problems like these, you just have to worry about writing the expression and coming up with 0, 1, or 2, or in very rare cases, a half, or maybe even a -1. But you'll be able to deal with those if you know how to do the 0, 1, and 2. So that's going to be our task. What is the exponent here in the rate law expression? And I said exponent because I'm going to deal with them one at a time. I'm going to deal with the bromoethane first. So I'm looking at the bromoethane, and I see in trial 1 it has this concentration, and the hydroxide has a 0.1. Now in trial 2, I see they haven't changed the hydroxide, which is great because I don't want to think about the hydroxide. I don't want that to mess up with my rate. But I see that trial 2 has doubled the concentration of the bromoethane. That's what you want to look for. Okay, this is a nice doubling. So I'm going to move up a bit, and we're going to focus just on trial 1 and trial 2 because that's going to help us find this exponent. Well, I find that the trial 2 is double that of the concentration for trial 1. Then I compare the rates of those two. And this is my comparison. I'm taking my rate, which is 9.5 for trial 2, and I'm dividing it by the rate in trial 1. And notice this comes out to a 2, and you probably should have been good enough to realize that indeed it is 2. So the concentration of the bromoethane, while the hydroxide is constant, is doubled. The rate doubles. So we can say when the concentration is doubled, then the rate doubles. 4.75 times 2 is 9.5. That the two are locked in place by the power of 1. If you triple the bromoethane, you triple the rate. If you cut the bromoethane concentration in half, you would cut the rate in half. And as a result, we can say that the rate of a reaction is equal to some constant, we'll get to that later, times the concentration of the bromoethane raised to the first power. So if this is doubled, the rate doubles. If this is tripled, the rate triples. So if the change in concentration is proportional to the change in rate, you know it's raised to the first power. If you double the concentration and nothing happens to the rate, then you know the bromoethane is useless, and you can give a 0 for its exponent. But that's not this case. 0 is a possible answer if we found out that changing a concentration has no effect on the rate. All right, so we've got half this problem taken care of for the rate law expression. We know that the bromoethane is important, raised to the first power. Well, we still have the hydroxide. Remember, this is going to be a 0, 1, or 2, and that's what we're going to look for next. We want to see something where we can deal with the hydroxide and see how it changes the rate. Well, here I see all my hydroxide concentrations are 1/10 molar. There's no change there, so that's not going to help me. But on trial 4, I see they've tripled the hydroxide concentration. Well, I'm looking here and I see that my concentration of the trial 4 bromoethane is 0.5. Now, I am going to have things set up so that my bromoethane doesn't change. So I'm looking where the bromoethane doesn't change. Well, here's the bromoethane not changing. It's 1/2 and 1/2. So if I use trial 2 and trial 4, I don't have to worry about my bromoethane. I know it's not changing. So we want to eliminate the thing that doesn't change, that we're not worried about, the bromoethane. So we know that trial 2, we had bromoethane at 1/2 molar, and our hydroxide is 1/10. And on trial 4, the bromoethane is still 0.5, and our hydroxide is 3/10. So our hydroxide was tripled, and we didn't do anything to the bromoethane. So again, let's sort of look at things here. We are going to compare the rate at trial 2, 9.5. Trial 3 is 28.5. Well, your math is good. You'd end up being able to do that in your head, but you can see that the answer for this is 3 times. So the reaction rate increased 3 times when the concentration rate increased 3 times. Okay, that's nice and proportional. That's the same thing that we found with our bromoethane, that when you have the same proportion increase 3 times, it must be raised to the first power. So we know if we triple, quadruple, half our hydroxide concentration, we will do exactly the same thing to the rate. That's what this exponent 1 means. It means it's valuable and being directly proportional. Now I sort of revealed my next question. I now know that the rate is equal to a constant times the bromoethane raised to the first power and the hydroxide raised to the first power. That's usually worth 1, maybe even 2 points on an AP exam, because you needed to do this logic. Now let's go here and see and pick a rate and a specific trial. And the trial I'm picking has the one where we have our 2.8 times 10 to the 2.85 times 10 to the negative 3. Let me get this out of the way. Whoops, out of the way. This is our rate, and don't forget our unit. Our unit's going to be important. They're worth a point, very typically. When the rate is 2.85 times 10 to the negative 3 molar per second, it's going to be equal to the constant, which is what we're going to look for next, times the concentration of the bromoethane. Well, we know that is 0.5. So I'm going to put a 0.5 here. Molar, so that's its concentration. If we had pressure, we'd be dealing with atmospheres. But this is a liquid at room temp, so we're dealing with molar concentration. And then our hydroxide is 3/10 molar, raised to the first power. Well, this is chemistry, and chemists love math. And we can solve, and we also love constants. So we can solve for this K and find out what the critical constant for this temperature is for this reaction. I'm going to do the math. Here's how I do it in my calculator. 2.85 exponential entry negative 3, this value, divided by 0.5, and again divided by 0.3. And I get 0.019. That's my constant. My constant, my K, is 0.19. I'm solving for my K. Now, notice I had to include a unit. Now, if I look at this, I'm solving for K. I'm still going to have my per second as the denominator. I'm dividing by 1 molar. That cancels that 1 molar out, and then I'm dividing by another molar. So I now have an extra molar in the denominator. This is usually written this way. On an AP exam, you're going to get 1 point for the K and 1 point for the unit. So be very, very careful with your units. Now, this unit will be set up so that everything works out right when we multiply stuff out to get rates versus concentrations. So look at this unit arrangement and be sure you can figure that out. That's as important as this finding out the 0.019. This is the constant for this temperature for this reaction. No matter how you do this reaction at this temperature, whatever concentrations you've got, you just use this K and these concentrations, and you're going to know how fast it is. This is just an amazing rate law expression. So let's go for one more point, the last point on an FRQ that involves rate laws. Let's check and see what the rate should have been if during trial 3, 0.375 molar and 1/10 molar. Let's see what the rate is based on our rate law expression with this constant. Okay, let's scroll up and do the math. I'm going to scroll down and you'll see what I do with my TI, but before I do that, let's set up the solution right here. Since I'm plugging in my 0.5 here and my 0.3 here, and I know my constant, if I multiply 0.5 times 0.3 times my constant, which I figured out is 0.019, let's see what we get. Here's my calculator, my calculation for the constant. I'm taking my 0.375 molar here times my 0.1 times my constant. I didn't retype it in, and I get 7.125 times 10 to the negative 4. And look, that's the same result experimentally. This equation right here, the rate is equal to this constant, will be able to, allow you to find out how fast the reaction is going, no matter how you do it, no matter what your concentrations are for this given temperature. You can know how fast this is going to happen. You can confidently mix and say, hey, this is what's going to happen. Now, notice I have a molar here and a molar here. That 1 molar cancels out this per molar, and I get molar per second, which is a rate, which is how fast things go. A long problem, but this is a level 5 problem. You can handle this. You know some chemistry. So go to the WebAssign, which I have randomized. So you're going to have slightly different numbers, and see if you can solve it using this set of reasoning. Good luck.